be something like this, you know. What, I don't know, some kind of, let me draw some, I don't know. Maybe the surface looks like this. Maybe something like that, okay? Maybe something like that. So that, maybe that's the surface, okay? So this is z equal g of xy. And you do exactly the same thing. We have the same x naught and y naught. What we're going to do is we're going to approximate the g by, so here we go, this is the point on the surface, right? So this is x naught, y naught, g of x naught, y naught, right? And we're going to approximate that by some tangent plane as well, right? And so the equation of that tangent plane is going to be z equal g of x naught, y naught, and it's going to be generated by, you're going to, you know, slice this way and have a curve this way, slice this way, have a curve this way, and draw those tangent lines, and that creates the tangent plane, and so you're going to have this. It's the same idea, but you're doing the same thing for a different surface, right? So we have two of them. Okay, so what we're doing now is this describes, the red describes the plane. And what we're doing is we're going to approximate the original f of xy by the plane. We're going to approximate the original g of xy, and it's going to be approximated by the plane, the tangent plane. All right, so this is the tangent plane. And it's approximating him, and this is the tangent plane over here that approximates him. That is the essence of basically about, let's say, a third of multivariable calculus, right? That's the basic idea. Okay. Now what I want to do is I want to remind you guys, what does it mean to change variables? Okay? So what does it mean to change variables? So I'm going to go ahead and erase this, okay, because that's a prettier picture. So let's go ahead and talk about what does it mean to change variables. Okay. So, okay, so in general, so say you have something like this. Okay, so now what I'm going to do is I'm going to go downstairs and look at the xy. xy. Okay, so here is the origin, 0, 0. And if I choose an x naught, y naught, like for instance over here, all right, then this is x naught, y naught, right? And what I could do is I could draw a brand new axis. And this axis is going to be x tilde, y tilde, okay? And this guy is going to be the brand new origin in blue, right? So he'll be the blue 0, 0, but in x tilde and y tilde, right? So what you want to do is you want to go ahead and relate the original black x with the blue x tilde and y tilde, right? So if you're going to go ahead and relate them, it's pretty obvious, right? So for instance, let me go ahead and do a specific example, and then you guys tell me, okay? So say I have 0, 0 right here. Okay, and now let's say I decide that I want this guy right here, so this is the black. It is x, y. The origin's right here. And then right here, because this is 1, 2, this is x tilde, y tilde. Okay? So now tell me, what is this point? 3, 2. Okay, so now I'm going to say, suppose I have 4, let's see, 5, 6, and then 3. So say I choose this point right here. So in black, that is 6, 3, right? But tell me, what is its coordinate in blue with respect to x tilde and y tilde?
3, 1.
Right, it would be 1, 2, 3, 1. So in blue, it is 3, 1. Okay? So does everybody see the relationship? So it's actually 6 minus the 3 equal 3, right? And then what you have is 3 minus the 2 equal to 1. So does everybody see this? So what you have is you have your x coordinate, you subtract the x naught, and what you get is you get the x tilde. Does everybody see that? Okay? If you have the y coordinate, you subtract the origin, the y tilde, the y naught, and that's how you get your y tilde. Does everybody see how that works? So let's just find another point right here. So for instance, say I'm interested in, how about this point? Okay, so tell me what it is in black, in xy.
2, 4.
2, 4. Okay, so then what would it be in blue using this? So in this case it would be x minus the 3, y minus the 2, and then just looking at this, that would be the x tilde, y tilde. What would be its coordinate?
Negative 1, 2.
You plug in the 2, and it becomes negative 1, right? So you can see it's negative 1. And then you plug in the 4. 4 minus 2 is 1, 2, right? Now you can see it from the picture, but you can see it from this, okay? So the relationship is going to be the tilde, the new tilde coordinate is the x minus the x naught, the origin, the new origin. And then y tilde is y minus y naught, okay? Now, if you go ahead and you move it to this side, then what you have is x equal x naught plus x tilde, and y equal y naught plus y tilde, okay? So this is how you change coordinates. This is what we mean by change of coordinates, okay? So what we're going to do is, our goal is we're going to let the x naught, y naught be a stationary point of the system, okay? So what we're going to do is we're going to let the x naught, y naught be a stationary point in the system. And remember what we're working with. We're working with dx, dt, and dy, dt. Okay, this is what we're trying to do. And I said we're going to only deal with autonomous. So this is the f of xy. So everybody see that this guy right here is this surface, okay? And then g of xy was that other surface. That was, so this surface was approximated by this red tangent, and then I drew this other surface over here that was approximated by that red tangent, right? And the x naught, y naught being a stationary point, what does it mean to be a stationary point?
Dx over dt equals to 0.
Right, so if you plug it in, it equals 0. Exactly, exactly. Okay, so let me go ahead and say that. So this means that if you plug it in, f of x naught, y naught equals 0, and g of x naught, y naught equals 0, right? It causes this to be constant for all time. Okay. Does everybody see why this is so useful? Remember how back in the past, I'm going to say, go back to pre-calculus, right? Whenever we did point slope formula, okay? Remember how you do y minus y naught equal m minus m times x minus x naught? Remember this? Okay. Some calculus teachers, when they say, oh, find the slope of the tangent line, and they say, oh, you don't have to simplify it to y equal mx plus b. The reason why you don't simplify it from y to y equal mx plus b, because in reality, you think of a brand new line as going through that point, so this becomes y tilde equal m x tilde. So everything is actually y equal mx. Does everybody see why? That is the reason for slope formula. It's really y equal mx, okay? So if you took linear algebra, you see that's, just a times x. Okay, so now we're going to use this guy as our stationary point. So now what we're going to do is we go back to our nonlinear system. This is what we're working on. This is what we did. Okay, so I'm going to go ahead and I'm going to erase this guy, okay? So it's been here for a while. And what we have is, this is what we're trying to solve. And I said we're going to approximate him by the tangent plane. So this is the original height plus the slope evaluated at that point times the run, sliding up one of the tangent lines, and then you slide up the other tangent line in the other direction, right? So x naught, y naught, y minus y naught, right? And you're sliding up on the tangent plane to the point right above xy. And then this guy right here, you're saying this is the original point, this is the other surface, right? We had two surfaces. This is the slope, evaluated at that point, of course, times the run, plus the slope times the run, so you slide up, and this tells you how much you change in height in the other direction, right? But if we have stationary point, what does that mean for f of x naught, y naught? 0, right? Stationary point. If x naught, y naught is stationary point, then this is 0. And we only have that, okay? And then what we should do is we should go ahead and consider our change of variable. So what we're going to do is we're going to have our system x tilde is equal to x minus x naught, y tilde equal y minus y naught, right? So then this guy right here becomes x tilde right here. This guy right here becomes y tilde. This guy right here is x tilde, and then this is y tilde. Okay? So can you see how, this is our actual system, but we can see that this system is approximated by somebody that's linear, right? So consider this system. This system is going to be dx tilde dt, dy tilde dt, right? Equal, can you guys see it? It's going to be partial of f with respect to x, x naught, y naught. Partial of f with respect to y, x naught, y naught. Partial of g with respect to x, x naught, y naught. Partial of g with respect to y, x naught, y naught. And you have an x tilde, y tilde. Everybody see? This is what that is. Boom, boom. That's the first, and then boom, boom. That's the second line right there. That's this guy right here, right? And so now, when you plug this in, these guys are all constants, right? When you plug these x, right? So then what you ultimately get is you get this linear system. It is dx tilde, it's, dt equal ax tilde, right? where, you know what, I'll just write it instead of I'll write it with like bold. So that bold will mean vector. Okay, so you know how like the book writes it bold and then we usually go like that? Okay, so then this guy, when I write super bold like that, so x, this x is not that x, right? This is x tilde and this is y tilde. So does everybody see that this is like, usually we put a little thing over here. I can put him over here, but you know, if that helps. Just remember, that's him. So does everybody see? We have this, okay? So we go back to the most easy equation of all, and then there were like the 20 face plan portraits that you were supposed to memorize for this, right? Okay, and so what you have is you have this linear system, right? And this linear system approximates what he approximates is he actually approximates this guy, right? He approximates this. That's what he approximates. Okay, and just always remember that we have this. This is our change of variable right here. But let's rewrite that again, okay? So that's actually x equal x, add the x naught plus the x tilde, and y equal y naught plus the y tilde. So this is how you switch back and forth. Okay? So all I did was I just added that to both sides. Okay, so then the actual solution of the original nonlinear equation, okay. Let me see. Let me go ahead and erase this. So the actual solution of the nonlinear equation is going to be actually, so the original nonlinear is, remember, that's this guy right here is the original nonlinear system is right dx dt. Let me write it. Is dx dt f of x dy dt f of xy g of xy, right? So the actual solution, which you would write as x of t, y of t, right? That guy, he is approximated by, and you can see the solution of the linear system dx tilde dt equal ax, right? And so the way you would write it, of course, is this guy, x of t, y of t is approximated by x naught plus, so the solution of that guy, so this guy's solution, his solution is going to be x tilde of t, y tilde of t, right? That's his solution. So you have to add this, right? You have to change, switch back. Y tilde of t. Okay? But you have to deal with the change of coordinates right there. Okay? So this is the solution of the linear system. Right? Which approximates this. Okay. So when you have this then, the linear system is called the linearization of the original system. Okay? So the linear system above is called the linearization, just like what we did before. So the tangent line approximations were the linearizations of those surfaces, right? So what are we linearizing about? We're linearizing about the x naught, y naught, which is a stationary point, which is going to be a stationary point. We're going to linearize around a stationary point, okay? And the matrix A that I wrote down is called the Jacobian matrix of this guy right here, okay? So usually we write it like this. So this f of xy, this is the f of x, y, g of x, y, okay? So this f is not that x, right? This f is not that f. These are the two, this is the f, this is the g, right? So what we have is this guy right here. So you can rewrite this system as dx dt, right? So dx dt, this x is not, this is both these guys, right? And you write it as f x, like that, right? Does everybody see this? That would be how we would write it. So does everybody see this is x, and then this y, and then this is this x, and this y, right? And so what we're doing is we're taking him, and we're approximating him. We're going to use the linearization like this, right? Of course, this is going to be vector. This guy is approximating him. Does everybody see to a change of coordinates? Okay? So this Jacobian matrix, let me write it down one more time for you, okay? It's the partial of f, take the derivative of f with respect to x, the derivative of f with respect to y, derivative of g with respect to x, derivative of g with respect to y. What you do is you plug in the x naught, y naught, plug in the x naught, y naught, plug in the x naught, y naught, and you plug in the x naught, y naught, okay? And that is the Jacobian matrix. So this is the AX, right, that approximates this. So does everybody see what we're doing? Now, be careful. Last time I talked to you guys about the Hessian matrix, right? The Hessian was something completely different. That was, oh, by the way, this, you write it like this. You go like this, okay? It's only first derivatives. Remember the Hessian? The Hessian was this thing right here, right? So we actually took the integral, or we took the h, right? So we took the h, right? And this is a matrix of second partials. So you take the derivative with respect to x, and then you take the derivative with respect to x again. You take the derivative with respect to x, you take the derivative with respect to y. You take the derivative with respect to y, the derivative with respect to x, y, y. And I cannot remember. What did I say the h was called?
Hamilton.
It was called what? Hamiltonian. Thank you. Yes, the h is the Hamiltonian. Okay. So remember, it's the integral of the orbit equation. Hamiltonian, or the integral of the orbit equation. Okay? And this was assuming we could integrate. This whole thing is if we can't integrate. Okay? So then this is what we do. We linearize. And that was the whole idea of calculus in the first place. The entire idea of calculus is linearization. There are whole swaths of mathematics. The other two areas of mathematics do not involve linearization. Okay, this is just one small area, and it's important enough to spend a lot of time in. But if you're into math, you will learn many other areas where that is not the main idea, but this is the main idea of calculus. Okay, so then what that means is your phase plane portrait. Let me get this lower for myself. Your phase, if you're linearizing, and it's like, it looks like that nearby, right? So the whole point is that the surface looks like the tangent plane, right? Or the curve, the complicated curve, looks like the easy straight line, all right? And if you change coordinates, you make it real simple. You get rid, you don't have the mx plus b, you don't have that extra constant, right? So what we have is we have a phase plane portrait near the stationary point, right? X naught, y naught. and we have the phase plane portrait near the origin, right? That's going to be our new origin. And so this is the phase plane portrait of the original near this. It's going to look like the phase plane portrait of this tilde system. Right? Near its origin. And its origin, of course, is going to be, right, this guy is going to be its origin. But its origin is actually this guy, right? So remember, this guy is the Jacobian matrix. Evaluated at x naught, y naught. And that is the idea. So here's the original system. This is the linearized system, and that's where we spent all this time learning the linearized stuff, okay? Now, this is true when the determinant of the Jacobian does not equal 0, okay? So that means that nearby it's 1-to-1 and invertible, okay? So that's the main idea. Okay, so let's go ahead and just kind of talk about, sort of just some details about this, and then we'll actually do it. And then tomorrow we'll have stories and actually, do more of that. Okay, so what you do is essentially, assuming that, we want to say the determinant of the A. So for all these cases, we need to assume that the determinant of the A, now remember the A is the Jacobian. This is how you write the Jacobian, right? And you're going to go ahead and you're going to evaluate it x naught, y naught. The determinant A does not equal 0. Okay. So we had two real eigenvalues. Remember, we had both positive, both negative, one positive, one negative. Do you remember in the linearized system, what was the phase plane portrait? What was it called? It was called a nodal source, right? And what is this guy called?
Nodal sink.
Nodal sink. And then what else did you have? Saddle. Okay, so this is what it would look like in a linearized system at the origin. Okay? And so in the actual original system, the actual system that we're trying to, it looks similar. Similar near, and remember the x naught, y naught was the stationary point, which with the change of coordinates would be at the origin, okay? Now, you want to be real careful when you find these guys, right? You have an eigenvector, v, right, corresponding to some eigenvalue. So when you do this, right, you have I'm going to just say, pretend this is your eigenvector, okay? So your eigenvector line, is y equal mx. And does everybody see this is change in y, change in x? So it's going to be y equal v naught over x naught x, right? But over here in the original system, what you have is the orbits are going to be tangent to this line, okay? So remember, we're going to change the coordinates. So y minus y naught goes here, v naught over x naught, x minus x naught, okay? So it's going to be always through the point, so x naught, y naught, because that's your origin, right? So this is how you would write it over here. Okay. One real eigenvalue. I'm just going to go ahead. Hopefully you guys had a chance to look at it in the book. if it was one real eigenvalue and it was negative, let's say characteristic, in the characteristic equation it was multiplicity 2. So then if it was negative, this was called a radial sink. And this was called a radial source. Okay, and so what you have over here is you have every half line radiating from the x naught, y naught, has an orbit tangent to it. Okay. If you had over here, one of the other ones was one real eigenvalue with multiplicity 2. Let's see, that was the multiplicity 2, so let's make this multiplicity 1. Okay, so then what you have is if it was negative, it was called a twist sink. And positive, it was a twist source. And you also had counterclockwise and clockwise. Okay, the orbits over here, again, are tangent to the line through x naught, y naught in the direction of the eigenvector of the linearized system. And the counterclockwise and clockwise all match, as you would expect. If you had no real eigenvalues, what you have is, remember, we had lambda equal a plus or minus bi, right? As long as the a is less than 0, what do you have? Spiral sink. If the a is greater than 0, it's a spiral source. Exactly. All right. Again, you have the counterclockwise and clockwise that you deal with, that I showed you how to do last time. And over here, it's similar. Okay. So you have something similar to it, and the counterclockwise and clockwise match. Okay. And then if the origin is a center, in order for all of this to work, all right, you must check that the original system is conservative to make sure that the center, that you get a center over here, all right, in the actual system, okay? So one of the things you'll have to do is double check that the original system is conservative, okay? Then you are guaranteed that it's going to be similar to this, it'll look just like that, okay? And then the other guys, the other ones all involve the determinant of a Jacobian being equal to 0. Okay, so these were the other things, so I didn't have time to go over it, but they were the linear sink. Hopefully you had a chance to look at them. Linear sink. I'm not going to emphasize them on the test, so you don't have to worry about this. Source, 0, and parallel shear. And this is when the eigenvalue equals 0, and you have at least one line of all stationary points, so they're not isolated. So they're not isolated. And that's the reason why we wanted the determinant of Jacobian to be 0. Okay? Okay, so then just want to say, go over the dynamical stability of a stationary point. And remember we said it's stable if every solution starting near it stays near it. Otherwise, it's unstable. Detracting if every solution starting near it, but not at it, approaches it as, you know, the t goes off to infinity, right? So it's attracting. And if it is repelling if every solution starting near it, but not at it, you know, moves away from it as t goes to infinity, okay? So just always do a stability analysis for me. And just notice, right, obviously if it's attracting, you know it's going to be stable, right? And if it's repelling, obviously it's unstable. But you could have somebody that's not attracting, not repelling, right? And like a saddle, and that was unstable. Okay. Anyways, let me just go ahead. I'm going to just let you guys take a look at that in the book. But remember your linearized system. Let me just write it down again. Okay. Your linearized system was this: dx tilde, dx tilde dt, dy tilde dt, right? Equal Jacobian, evaluate at x naught, y naught, y. So the derivative f, derivative g with respect to x, derivative g with respect to y, and you evaluate at x naught, y naught, x naught, y naught, right? You go x tilde, y tilde, right? Your original system was this: dx dt, dy dt equal f of xy, g of xy. Okay? Remember, you can write this as dx, now this is going to be a vector, equal ax tilde. Okay? You can write him as dx dt equal f of x. Remember, this is x, this is xy. Okay? So that's the linearized system. This is your original system. Okay, and what you have is that the stability all matches. Okay? But always, whenever you deal with the center, you gotta check that your original system was conservative. Okay, so just as an aside, because of that, notice that if you have an integral h of xy with non-degenerate critical points, what we had here was that all the stationary points, and we did this, last time we met, they're, what you have are saddles or centers. So automatically, if you have, if linearization shows the stationary point is not a saddle or center, the system does not have integral h and is not conservative. Okay? So, if you have something beside a saddle or center, automatically you know it's not conservative. Now, if the linearization has this saddle or center, you absolutely still need to check that it's conservative in order for the original to also be like that. Okay? So let us go ahead now and actually do a problem. This is the problem we did last time, okay? We did it using the Hessian. Now we're going to do it with the Jacobian, all right? So let's go ahead. Okay, you take a look at this. Okay, so in order to do this, your first step is always find your stationary point, right? Find stationary. So everybody see how this is nonlinear? That was the core, right? Nonlinear. And, you know, even if you could find, you know, the answer, it's very, very difficult to understand, right? So what we do is we want to get a phase plane portrait to understand what's going on. So we're going to find the stationary points, right? So what you do is you set, you know, the derivatives all equal to 0. So I should go ahead and write it out. dx dt, dy dt, right? You set these guys equal to 0. And last time we figured them out, so I'm going to go ahead and make sure that we don't waste time doing that. So there they are, okay? Now, I want you to, so let's go ahead and now figure out how you do the Jacobian. Okay, so remember, the way you remember what the Jacobian is, you look at this guy right here, right? Now your f, so you see how this whole thing can be written as dx dt equal, so remember what it is. It's f x, okay? So what it is this is the f of xy, this is the g of xy, right? And so this is the f of xy, this is the g of xy. Okay? So we have this, let me write that down. That is the y 4x minus x cubed. Okay. And so this person did not come. Okay. And now what we're going to do is we're going to write down the Jacobian, right? So this is the Jacobian matrix. The Jacobian matrix is take him, you write it like that, that's the Jacobian matrix, okay? And you write the derivative of the f with respect to x, the derivative of f with respect to y, derivative of g with respect to x, derivative of g with respect to y. Okay? And let's go ahead and do that. So let's look at this. This is f. What is the derivative of him with respect to x? 0. What is him with derivative with respect to y?
1.
That's actually pretty easy. Here's the g. Derivative with respect to x. 4 minus
3x squared.
Good. Derivative with respect to y.
0.
Okay, that's very nice. Okay, so there we go. Okay, that's your Jacobian. Now what we do is we're going to linearize around every single point, right? So what you do is we're going to look at the Jacobian around 0, 0. Okay? So around each stationary point. Does everybody understand what we're trying to do? This guy right here is the A. Okay? And what we're doing is we're going to do dx tilde dt equal ax tilde. Okay? And we're going to go ahead and solve him. All right? And the solution to him approximates the solution to the original near the stationary point. So we go ahead, and this is the A, and we plug him in. So you can see just plug in the 0. This is the X, this is the Y. You plug this in, and so you have 0, 1, 4, 0. This is not the Hessian. We did it a different way last time. That was for conservative systems. This is, I'm doing the same problem, but we'll do other problems, okay? So does everybody see this? So you look at this really quickly and you say, and then now you have to be swift. So you say, okay, what is the characteristic equation? P of z is z squared. What's the trace?
0.
And what is the determinant?
-4.
Okay. And so what you have is z plus 2, z minus 2. What are the eigenvalues?
2, -2.
Okay. values lambda equal plus or minus 2. Okay, right then and there, what are you going to have near the origin? Saddle. Two different sides, so you have a saddle. Okay? So what it's saying is you're going to have saddle for the linearized system, and the linearized system approximates the original system, so you're going to have a saddle nearby. Okay? And give me a stability analysis. Is the saddle stable or unstable?
Unstable.
It's unstable. Is it attracting?
No.
No. So it's not attracting. And is it repelling?
No.
No, because there's one direction that brings it in. It's not repelling, not attracting. Okay? And now what we need to do is find the eigenvectors. So we use Cayley-Hamilton. Cayley-Hamilton is the characteristic polynomial annihilates the matrix, right? So now you just go ahead and say A plus 2I, A minus 2I equal to 0 matrix, right? You go ahead, just go ahead, write this down. So go 0, 1, 4, 0, 0, 1, 4, 0 equal 0, 0, 0, 0. Okay? So let's go ahead and let's stick this in. So this is plus 2I, so plus 2. Plus 2. This is minus 2, and this is minus 2. Ah, it's bad. Let me get a better one. Okay. So having done that, plus 2. Okay. So really quickly, so this becomes 2, 4, 1, 2. This is negative 2, 1, 4, negative 2, and 0, 0, 0, 0. Okay, tell me what are the eigenpairs. So let's start here. So what is the eigenvalue from this side?
Negative 2.
Negative 2. What is the corresponding eigenvector?
Negative 1, negative 2.
Choose the easier one. 1, negative 2. And make the top one 1 if you can. Okay, so that's the eigenpair for this side. Eigenpair for this side?
2.
2. What's the eigenvector?
1, 2.
1, 2. There you go. Okay? So then you can write down your lines. Okay? So does everybody understand that? Okay, so in the tilde system, what this is y tilde equal minus 2 over 1 x tilde. Okay? And then you convert back into the original system. Now, if this was some other number, then you would have written y minus that other number, minus 2 times x minus that other number. But since it was 0, 0, it was okay, so it stays the same, so it's y equal minus 2x. So this is the eigenvector line. Does everybody get that? And then similarly here, you have y, change in y over change in x. So 2 over 1, x tilde. And then, if this had been like 3, 5, you would have said y minus 5 equal 2 times x minus 3, right? So y minus y not equal 2 minus x. But just because it was 2, okay, so this is this guy right here. So you can eigenvector lines. Okay, so you were going to be able to give that. So now, let me go ahead. Let me go ahead and do a couple more. Okay. So we did the first one. Now we're going to do the next guy. We're going to we're going to linearize around 2, 0, another stationary point. Again, what are we doing? This guy is the A, okay? And this is dx dt equal A x but tilde in the tilde system. All right, linearized around this, and this tilde, the origin is the 2, 0, right? The origin is the 2, 0. So let's go ahead and write down the A. Okay, so now you plug in 2, 0. So this one's easy. So if you plug in 2, it's not so big a deal. So what is the answer over there? What do you have? Plug in the 2. Minus 8. Okay. So there you go. And so now let's go ahead. What is the characteristic polynomial? P of z. Trace is 0. And so this is plus 8. So right there, what are the eigenvalues? Yes. Lambda equal plus or minus 8 root 8I, right? Root 8I. Okay. But with pure I, what do you have? It's a center in the linearized system. Then what you do is you say, I gotta double check that it holds as a center in the original. So you have to make sure that it is conservative. So check conservative. So the best thing is to see if it's Hamiltonian or check exact, right? So let me ask you guys, what is the test for exact? Partial of f with respect to x, partial of g with, remember we have an easier check, it's this guy, right? This is much easier than the n and the m and then writing it in orbit. So let's go ahead. Take the derivative of the f with respect to x, and what is the answer? 0. What is the derivative of this guy with respect to y?
0.
So 0 plus 0 really equals 0. So it is exact. So therefore, the original is actually a center. All right? And so now what you have to do is say, well, let's figure out the tangent. What the tangent is, because we need to figure out, is it counterclockwise or clockwise, right? So if you look at this guy, all right, and you go dx dt, sorry, tilde, okay? And you plug in 0, 1, minus 8, 0. And we're going to plug in 1, 0 in the tilde system. You get 0 minus 8. Well, if it's 0 minus 8, okay, this is in the tilde system, this is in x naught, y naught. You're pointing down, so is that clockwise or counterclockwise? It is clockwise. Okay, so you have to always, when you have a center, clockwise. Give me a stability analysis. Is it stable or unstable? Stable, because if you start nearby, you circulate and you stay nearby. Is it attracting? No, it's not attracting, and it's not repelling, right? It's stable, but neither attracting nor repelling. Okay, so there we go. Okay, and now what you do is you do the same thing again for your third guy. So you see why it's important to know all this stuff? So now you go minus 2, 0. You do the same thing. It turns out that the A is exactly the same, right? So you plug in the square, you get this. So all the information stays the same. So in this particular case, you have a center. It's going to be clockwise, so you should write all the stuff down. And of course, we knew it was conservative. So then the actual is like this as well, and it's stable, not attracting, not repelling. Okay, so now we have more detail here, and we can finally just draw the picture. Okay? And so the picture is this. So here's your original. So here's the original. You're going to have the origin right here. 1, 2. You'll have another origin right here. You'll have another origin of another system. Okay? So for your linearized system. So let's do the one at the origin. So right here, what you have is you go over 1, down 2. So over 1, down 2. Back 1, up 2. So does everybody see this? So this, with this one, now are the arrows pointing in or pointing out? Because it's negative. So they're pointing in. Okay? And now the other guy, go over 1, up 2. And pointing in or pointing out? Okay, so now, does everybody see now? What you have is this is your saddle, and you can see the direction of the arrows. And later on, we'll have a story of a predator or prey system. You know, what happens, you know, does one species go extinct? You know, what happens, you know. So we'll have a story associated with all this, but for right now, this is not that. Okay, and then over here, at both of these, we have clockwise. But you see, this makes sense, right? We have a clockwise center. Clockwise center. Okay? So you can see now what's happening is it's like this, so I should draw this. I use red to draw mine. Okay, so it's gonna be like this, right? And what's happening now, we wanna be careful. What's happening is we have this. And so you can see it's gonna be like this. Draw your clockwise and you'll see, yes, it kind of goes like this. And now you can see, yes, all these arrows actually make sense. They all line up properly. And then it's like this, right? And then it comes in like, oops. So it comes in as close to this, it's very close to this. And it comes out like this, and it comes over here. And so what you have is you have several like this. Okay, so you can see what's going on here now. So this is when you have something, it goes like this, and then it goes like this. Okay, but it doesn't touch the acid. It's asymptotic to this. It goes like this. So this goes like this. Okay, so this. Okay. So does everybody get the idea?
Do we need to know where they?
Sorry?
Do we need to know where they?
Well, they meet right here in the origin, and they're not touching, right? None of them are supposed to intersect. So that is just a sketch of your face plane portrait. Yes.
How exactly do you get the direction clockwise or counterclockwise from that vector?
You always look at the original matrix because this is the tangent vector.
Right.
Okay. So then this is the new origin, right? Which is actually 2, 0. Okay, but it's the tilde origin, 0, 0, 0, right? And so what I do is I plug in, what what would be 1, 0, but I would plug in 2, 0, okay? So, I mean 1, 0. So this is in the tilde system. I plug in here, and then I get this, and so what is the tangent? 0, -8. And so then the curve goes this way, right? This is clockwise. Okay, if it pointed up, it would be counterclockwise. Okay, let's do something a little bit more complicated. Let's do this guy. Okay, so what you do now is essentially the same thing. Okay, so actually, why don't I just because let's not even do this. Let me skip to a cool example. I mean, the one that we have is a cool example, but I think what I'm going to do is maybe I'll give you a story. So what time do we have right now?
7:47.
Sorry?
7:47.
Oh, 7:47. But actually, does everybody see the main idea? Do you want to just go ahead and practice this at home? And then tomorrow we'll do predator-prey systems, competitive systems, cooperating systems, and then we'll see what